The Chatelier's principle. So the idea with the Chatelier is that we're looking for a qualitative way to describe which way a reaction will proceed depending on how we change reaction conditions. Now, what Le Chatelier's principle is getting at is that if we have a reaction at equilibrium, meaning that we have the desired amounts of products and reactants in a system, if we do something to stress the system, meaning we add reactants or products, or we change the pressure, or we add or remove heat, the reaction is going to change to compensate for it. It wants to get back to that equilibrium condition, and I will either favor a forward or reverse reaction until it returns back to equilibrium concentrations. Now, when it comes to Le Chatelier, there are three recognized stresses. The first and easiest to intuit is concentration. So if we look at our first reaction back here, nitrous acid, HNO2, dissociates to give us H plus and NO2 minus. If this is run to equilibrium, we have the ideal concentrations of NO2, H plus, and NO minus 1. Or NO2 minus 1. So if we were to add more HNO2 to solution, what's going to happen is we've got way too much HNO2. Basically, we don't have enough products. And so the forward reaction is going to become favorable. So if we add reactions, we're going to drive the forward reaction and increase the concentration of products. But if we were to add something like HCl, HCl is a strong acid, it's basically going to create a whole bunch of H plus. By adding H plus to the system, now we've got too many products. And to compensate, the H plus and NO2 minus 1 are going to come back together to give you HNO2. We could also add sodium nitrite, NaNO2. By adding NaNO2, dissociates into Na plus and NO2 minus 1. Na plus is a spectator ion. By increasing the concentration of NO2 minus 1, we again will drive the reverse reaction, in this case reducing the pH by decreasing the H plus concentration. So if we add products to a system, the reverse reaction becomes more favorable, and we're going to drive the formation of more reactants. So that's the first idea with Le Chatelier. If you add products, you're going to drive the forward reaction and create more reactants. If you add reactants to this products to the system, you're going to drive the reverse reaction and create more reactants. And this is a good way to drive a reaction to equilibrium. So if you want to completely remove all the NO2 minus 1 from solution, all you have to do is add a whole bunch of H plus. And basically, you're going to eliminate as much NO2 minus as possible in order to compensate for the additional H plus. Now, related to this idea of concentration is the second stress, which is pressure. Because we can relate pressure to concentration. We have the ideal gas law, PV equals nRT, and if we just look at moles over volume, that's concentration. That's just P over RT. Now, with gases, we're going to look at the moles of gas on the left and reactants versus moles of gas and products. So for our second reaction, 2 moles of NO2 go back and forth to N2O4. Because there are more molecules of gas on the left than molecules of gas on the right, if we drive the forward reaction, we will effectively decrease pressure. So if we have an equilibrium reaction, gas phase reaction of NO2 and N2O4, and we start compressing it, increasing the pressure, what's going to happen is that the reaction is going to create more N2O4 to compensate. It wants to get the pressure back down. So it's going to favor the side with less gas molecules. If we were to decrease the pressure, go the other way, what's going to happen is we're going to convert more N2O4 back to NO2 gas. And again, this is because it wants to get the pressure back up, and it's going to favor a reaction which increases the molecules in the gas phase. Now, don't take this to mean that if you increase the pressure, you always favor reactant. You always favor products. If you decrease pressure, you always favor reactants. It depends on the reaction. So if we look at the second reaction, H2 plus CO2 goes back and forth to H2O and CO. There's 2 molecules of gas on the left, 2 molecules of gas on the right. So if we compress this reaction or we decompress this reaction, we're not going to favor the reaction one way or the other because there's no change in pressure associated with this reaction. The second aspect, therefore, of Le Chatelier's when it comes to pressure is to recognize that if you increase the pressure, you're going to favor the side of the reaction with less moles of gas, less molecules of gas. And if you increase the pressure or decrease the pressure, you're going to favor the side that has more molecules or more moles of gas. Now, the third aspect of Le Chatelier's principle is the idea of temperature. So let's say we take carbon, add CO2, and we create carbon monoxide. This reaction has a delta H of greater than 0, which means that it's an endothermic reaction. It gets cooler as it moves along. So as we start heating this reaction, we supply heat to the system. The system is going to try to compensate. It wants to get the temperature back to the equilibrium temperature. And so it's going to basically, if we start heating, go forward. It's going to produce more and more carbon monoxide. If we start cooling this reaction, it's going to want to release heat, and so it's going to go the reverse direction. It's going to convert carbon monoxide to carbon and CO2. And that's the third aspect of Le Chatelier's. If we have an endothermic reaction and we supply heat, this is going to drive the forward reaction. If we have an endothermic reaction and we remove heat, we're going to drive the reverse reaction. It's going to be reversed for exothermic. If we have an exothermic reaction, we start heating it, we're going to drive the reactants. If we have an exothermic reaction, we start cooling it,
we're going to derive the products.